Alright, so let's create a cantilever beam, which is a common structure, and do a finite element analysis using Creo Simulate. So I'll begin first by creating a part, my cantilever beam. Okay, okay. I'll make first my the top view. I'll make sketch simple rectangle. Okay, like this, and I give dimension here. Let's say 100 millimeter. And then I'll give this width to be 20. Okay. Then I'll add a thickness in this sketch. Let's extrude this and make, let's say, 2 millimeter, 1 millimeter. I did by hand calculation similar to this. Let's say 1 millimeter. Okay. And I have this flat region. Okay, then save. Desktop. Okay. Okay, saved it. Now this geometry, I have, if I prepare model properties, I can check the model properties, the unit here. So if we want to change the unit, I go here, millimeter Newton second. Let me make this, okay? That's the default change. Change millimeter second, set. Yes, I'll interpret one dimension to one. Okay. Close. Okay, now it's changed the unit. I'll leave the rest as it is. Okay. Close. So now let's inspect. Go edit, definition. So that's now in millimeter. This is 100, this is 20. Okay. Now what I'm gonna do is, to simulate, all that I need to do is go to application tab, Creo simulate. Okay, in this case, what do I need to do? I need to add fixed boundary condition here and apply a load here. Okay, so first I'll select this region, this surface. Okay, and then displacement boundary condition, I will set this to be this constraint 1 as the name. Member set, and the surface is selected already. Because it's selected, you will see it here. So I don't need to change anything here. It doesn't even allow you to do that. So translation and rotation, we just said okay. Okay. Now this is fixed. The next thing is the world coordinate system will show you the direction to put in the force. Now I will add a force. I'll add a force on this. Okay. And the force direction is, I will put in the y direction, which is this direction. So in the y, let's say I'll put 0.1 Newton, but in the negative direction, so I'll put negative 0.1. Okay, and the unit is already Newton, so I will keep that. Okay, if you see that I applied 0.1 Newton down. Okay, now the next thing is I need to assign material. So let me assign aluminum material. So I pick material. So in this aluminum, this aluminum 6061 is a common material. Brass, bronze, copper, epoxy, iron. So out of this, let me select this. Okay, AL6061. Okay, then assign material. So this is already aluminum selected. Okay. Okay, when you do it, the material is already assigned here. Okay, we have the boundary condition fixed. We have material. We have the load. Now the next thing to do is that to make a simulation. So we've used this part, use the constraint, we use the load, and the next thing is we are doing structural analysis, not thermal. Okay, so here is the model setup, bounded condition. This is used for setting up, so you don't need to change anything now. So the next thing is we run the simulation. Okay, then we basically run. We don't have the simulation yet. That's the result. So let me close that first. Okay. Define, analyze, and analysis and studies. So I open that and go to file. Here we have new static, model analysis, buckling, fatigue, dynamic, all kinds of. Now we will be using only static. So in this analysis, we will not take inertia relief or nonlinear. Keep everything as it is. Takes the constraints. The load is taken. Convergence method. Just leave this as it is. First time. Okay. Now it starts the analysis. Okay. I didn't start, so I need to run this green. Also for analysis, they must be removed. Yes. No. It's running now. Completed. Now we will see our results. Okay, the result you can see here, view results. And here, template, another one. So let's see this. Okay, in window 1, the analysis result as a fringe, stress, and the von Mises. Okay, sure. So now you see the von Mises stress. So we get 2.9 megapascal of stress around the cantilever beam, and less stress, very small stress, which is 0.0025, almost nothing compared to this one. 200, almost 1,000 times less than here. So the maximum stress occur here. So that makes sense physically, and if you zoom closely, you also notice something. The neutral plane. In the neutral plane, the top part will get, let's see, a closed version here. Okay, the top will have maximum stress, the bottom will have maximum stress, and the neutral plane has 0, which is what we know from other studies, okay, from mechanics of material. Okay, uh, so that's one result. We can also see displacement, the displacement magnitude. As let's see the displacement, we get 2.1 e to the power of minus 3 millimeter here um, at the tip, because this is fixed and you don't see large displacement here. It's a very small, 10 to the power of minus 10, because it's fixed boundary condition. Okay, all right, and here we see large displacement at the surface. So because of the mesh and because of the mesh, that our results will be different. Fine mesh, coarse mesh. Okay, I think that's enough. Okay, let's see. So you can watch analysis. These are all. Once you generate this result, you can just create you can see analysis result in different ways. You know, all probably in this way it's good, because you can show deformed shape in its form, displacement. This is the stress. This is displacement, and so on. Okay, I think that's enough. Thanks.